So the detector here, as I said, is a microton plate in my case. So it should give you I already give you an example of what it looks like. So what it looks like, the measurement of one electron energy loss spectrum, it looks like that. This is basically the sum of 10 spectrum repeated at the same conditions, and you get same condition, you repeat it just 10 times or 5 times in this case exactly, and you get by the sum here a smooth spectrum where the noise is reduced, kind of cancel out. So one sweeps gives one spectrum, one electron energy loss, where you can get the intensity. It contains about information about excitation levels. Here is the excitation level, which is the inelastic part, and here is the elastic part. The difference between inelastic and elastic is easy. So the inelastic part means there is a transfer of energy from the incident electron to the internal state of the atom, which is here argon. So there is a change of the internal state of the atom, so the electronic shells, for example. And here the elastic part means that that's the outer which is affected, so no internal state but external state of the atom argon. So basically there is no change in the atom itself. If you analyze if you want to know about the resolution of your system, you can use this structure here. If you analyze this structure and you can see details related, for example, to the vibrational excitation, which should be here between the ionization level and the elastic beam, the elastic scattered beam, then you have a good resolution. If you can see some structure like that or the vibrations of the molecule, it means you have a good resolution. So here I don't show a measure of all of this gas, but I did with the equipment. Even I don't show you some gas, air, argon and nitrogen. I will just present for air and argon. For the argon, you have the electron energy loss spectrum, and for the total cross section, I will show the one of air. So this is the protocol, how to get the total cross section, sigma total from the electron energy loss spectrum, which is here. The total cross section, one should know, is related to the intensity of this primary beam. So if you focus here, which is what we are going to do for the total cross section, we just focus on this elastic beam and forget about this part. And how this intensity varies as a function of pressure of the gas introduced give us the total cross section. In other words, the protocol is you put 1 or 2 millitorr of the gas of interest and measure a second yields, second electron energy loss spectra. Then, for example, here, and then you put another 1 or 2 millitorr more, and you measure a second electron energy loss spectra. You repeat this step until you add it for the to the background level 10 or 20 millitorr in order to have, for more or less 10 points. So here, for example, this is a measure for each peak. We record the maximum intensity spectrum versus the air pressure we introduce by reading the manometer, which is MKS brand. So here's intensity. So for the lowest pressure, we have the higher intensity, and for the higher pressure, we have the lowest intensity, because the pressure of the gas, if it is high, means the beam is attenuated. And if you use the formula we presented above, you can calculate the cross section, which is represented here, which is well fitted, and you have 6.17, which is very close to publication, because we have between 7 and 6, which is very good. Afterwards, yes, as I said, you put the data in a table, as I did here, and you present it like that, because you have to present your data need to be in Pascal, basically millibar, and intensity here is your counts of electron. Using the exponential formula, you can calculate the total cross-section. And now the question is, why is it important to use this total cross-section? So in order to predict, for example, how human tissue interact with the electrons or photons in radiotherapy, you need the total cross-section among other cross-section to predict how tissues or molecules within the body, like DNA components, will react. Also, in astrophysics, you measure the spectrum in the interstellar space or other location, and then you compare the spectrum, this is the electron energy spectra, with a database to identify the presence of a gas or a liquid, a specific liquid. And then if this electron energy spectra correspond to a data found, to a measurement did in the interstellar space, then it means you have argon there. And if you have the total cross-section, you can also predict how electron or photons will interact with air, for example, contained in the lung. And this is used, for example, in radiotherapy. For tissue, you need components like DNA. So here I just added a MATLAB code where you can gives you the structure of the code to extract from the yields, the spectra, the total cross-section. So here we use, in this condition, a pass energy of 58, and between the outer and the inner hemisphere we have 61 eV, and analyzer has 108 eV, and accelerating energy was 173. Yes, 173. Here you have the pressure, which you convert it to Pascal, millibar exactly, and then you feed your data and you put the coefficient component, and then finally you get your data. So I would like, before ending, to cite first a good reference which guided my presentation, which is Excitation of Molecules by Electron Impact by Strashmar from California, which is an old paper. And then would like also to thank my professor, which is my supervisor in Madrid in Spain, Professor Gustavo Garcia, which is the director of the Laboratory of Interaction, Radiation and Matter, and it's based at the Instituto de Física Fundamental. Thank you very much, and I think I hope this presentation will be helpful to those interested for electron scattering or proton scattering or any particle interacting with a gas or even liquid or solid, interesting in the concept of understanding better the concept of total cross-section. And that's it. Thank you very much, and bye for now.